In the previous slide series, we had a look at using z-scores and t-tests when hypothesis testing with one sample and with data that is parametric. In this slide series, we are going to stay with one sample test, but we are going to start looking at when our data is non-parametric. We're going to have a look at a different test that's known as chi-square, and that's used when we are hypothesis testing with our non-parametric data, or what we call categorical variables. Now, one sample chi-square test is referred to as the goodness of fit test. What it does is it actually assesses how well the sample data fits with the known parameters of the population. There are a number of assumptions that we adhere to when we're thinking about this. The first one is obviously that the data is categorical. The second is that the observations are independent, so there is one result per subject. The third thing is that there are sufficient categories to deal with all responses. So if somebody responds to a survey question, their response can actually be recorded because there's a category with which their response to go into. And also that the sample is sufficiently large. This equation here is actually what the chi-square test looks like. So here we are dealing with, as we described, we're dealing with our observed values and what the expectation is, so what the actual values are within the population. So we deal with those two sets of numbers. And what we're going to do is we're going to have a look at that in an example. So if we take an example of looking at industry in which people work within a given country, national survey data suggests that 10% of people work within primary industries, 30% within secondary industries, and 60% within tertiary. So the population is large. That is what the industry working structure looks like. The question we have is, how does the distribution of the industry in which people work within our survey sample, so we've gone out and we've done our own survey, how does that compare to the distribution that is shown nationally? To do this, we set up our hypotheses. So our null hypothesis is that there's no difference. Okay, our alternative hypothesis is that there is a difference. We set the significance level at the 0.05 level, so that's a 5% level, and we have a sample of 100, so we went and surveyed 100 people to find out what industry they work in. Now we can apply the test to our sample. The first bit that we have a look at is our degrees of freedom. Okay, so that is 3 minus 1, which equals 2, and that is of course 3 being the number of possible observations, so that's primary, secondary and tertiary, so those are the industries in which people could be in, minus 1, which gives us 2. Now for the equation here, we are having a look at the first set of figures relate to our tertiary figures, the second set of figures relate to the secondary, and the first set relate to primary. In the first set, we're going to have a look at the tertiary figures. We have a look at, it says 50 minus 60 squared, okay, divided by 60, and you can see that relates to our O minus E squared divided by E. This relates to the fact that we had 50% of our population worked within tertiary. We had an expected value of 60, given what the national distribution said. So we have observed 50 minus 60, our expected, we square that, and we then divide that by our expected value of 60%. We then add, or sum, as the large E, okay, which is basically a sum sign. We then add the rest of our possible cases together. So we deal with our tertiary, which is the first lot, secondary, which is the 45 minus 30. Okay, so we had 45 within our population. Okay, 45 within our population. They worked within secondary, minus 30, which is the expected value, squared, and then divide that by our expected value of 30, and then the same again for our primary. So we had 5 observed at 5, expected was 10. We square that and then we divide that by the expected value of 10. That generates 3 figures. That generates the first lot of brackets gives us 1.67, second lot gives us 7.5, and the third lot gives us 2.5. Add the whole lot together and we end up with a chi-square value of 11.67. So how do we go about interpreting the test? Our chi-square value is 11.67 at the 5% level of 0.05 with 2 degrees of freedom. We examine the tabled critical value of the chi-square test that corresponds to the test level of 0.05 and degrees of freedom 2. If we look those two things up in our tabled critical value, that gives us a tabled critical value for chi-square of 5.991. Our test statistic, 11.67, is larger than the critical value that comes out of our statistical table of 5.991, and so we end up having to reject the null hypothesis, and we can therefore conclude that the distribution of industries in which people work is in our sample is significantly different from the distribution that is seen in the national population. That is a chi-square test.